This talk is going to be about combinatorial problems, but it's largely solved with geometric techniques, mainly linear programs. And so I will take us through the problems that we solve, the problems in the field, and some of the really fun techniques that are often used to attack these combinatorial problems. Right, so today I'm going to talk about the online submodular assignment problem, and this comes from a generalization of online matchings. But before I begin, I want to say this is joint work with a wonderful set of grad students at the time. This is joint work with Daniel Hathcock at CMU, Billy Jin at University of Chicago, Kaylin Patton at Georgia Tech, and Mick Slotin at Weitzman. And this was presented at Fox 2024. At any point in the talk, by the way, please feel free to interrupt me with questions that you have, because I want people to, enjoy the proofs and understand what's going on. So I'm happy to answer questions as we go along. So this problem is originally motivated from online bipartite matching, which in turn is inspired from an application in advertising. So I'll say what the original inspiration and setting is. Ad slots are arriving online one by one. They're generated by, say, a query that a user has entered in, but basically an ad slot arrives, and when a slot arrives, it reveals a neighborhood of advertisers that might be interested in procuring that ad slot. When the ad slot arrives, you want to allocate it to at most one interested advertiser, and likewise, every advertiser can get at most one ad slot. Right, so this slot has arrived. We have to make a choice about which advertiser we allocate it to. So maybe I bring it down to this third advertiser. Second one arrives and reveals these two advertisers as a potential neighborhood, only one of which is available, so I match it to the second advertiser. Third one arrives, there are no available neighbors, and so I can't match it. Right, so online I have gotten a matching of size 2, but the best matching in hindsight was of size 3. Our objective is to maximize the size of this matching online. In terms of some benchmarks, it turns out greedy, which is just matched to the first thing available, is always going to be half competitive. And this just follows from the fact that any maximal matching is of size at least half a maximum matching. And this problem was beautifully resolved in 1990 by Karp, Vazirani, and Vazirani. And there's a 1 - 1 over E competitive algorithm. Now, let me just say for a minute, when I say something is a half competitive or 1 - 1 over E competitive algorithm, what I mean is that our online algorithm is getting something at least half that of the best thing offline, the best thing if you knew everything up front, right? So that's what these scores are: half competitive, 1 - 1 over E competitive. Okay, so that's the problem. This is the objective. Hopefully that all makes sense so far. Okay, good. So I know this is a geometry seminar, so let me say a bit about where the geometry lies. It lies in the power of these linear programs. So this matching problem, the problem of finding a maximum sized matching, is one that can be described beautifully with a linear program. I can have a variable for every edge, and then I have these linear constraints. Can people see my mouse, by the way? If I circle around, okay, cool. I have these linear constraints on the edges, right? The sum of these edges adjacent to a vertex I has to be at most 1, precisely describes the fact that every offline vertex needs to have degree at most 1. And you can say the same thing about the online vertices. And so in this way, I have a variable for every edge. I have these linear constraints that say that what I choose must be a matching, and I want to get the largest size matching. So this is a very continuous interpretation of a combinatorial problem. And what's beautiful about this polytope in particular is that vertices of these polytopes are actually integer points. That's not something you'd always expect out of writing a linear program, but matchings in particular are beautiful that way. And what's going to happen, the theme of this talk, the theme of these techniques, is that the geometry of the polytope is going to allow us to reason about combinatorial results. So that's where the geometry of this all lies. We're doing combinatorial problems, but we're going to use geometry to solve them. So I talked about the online bipartite matching problem, and it really kicked off a whole field of assignment problems studied in general. There's the edge-weighted variant, where you have values on edges and you want to get a max value matching. There's what's called the AdWords problem, where advertisers instead have budgets and they're bidding for potential ad slots. Then there's even more, the generalized assignment problem, which captures the 3 other problems I've listed here. They've all been well studied, and they all admit 1 minus 1 over e competitive algorithms under some assumptions. And furthermore, 1 minus 1 over e is the best you can get. This is an optimal competitive ratio. So in many ways, these problems have been resolved. But a key problem that me and my co-authors asked is, well, what assignment problems there have not yet been solved? A simple question, or a simple question that, to my knowledge, had not been attacked before our paper is just extensions of matchings to laminar constraints, which I'll explain in a second. There are coloring problems like online arboricity. Coloring is another type of assignment problem. There's scheduling problems like flow scheduling. And maybe to delve a little bit deeper into the problem definitions that I have just stated. Matchings with laminar constraints basically looks like the same matching problems that we had before, but now we have extra laminar constraints on groups of advertisers. So for example, these 3 advertisers can get at most 2 ad slots. This is still a matching problem. This is still an assignment problem. But when you add these extra constraints, the techniques fall apart. There's online matroid partitioning. And so let me take my favorite example of that, arboricity. Say we have let's say 3 colors, red, green, and blue. And edges of our graph are arriving one by one. When an edge arrives, you want to color it one of these colors. But we have the extra constraint that every color needs to be an acyclic subgraph. So we want to color as many edges as possible, but our colors have to remain acyclic. How many edges can we color? This is online arboricity. A similar problem, actually secretly sort of the same problem, flow scheduling. We have a network N, which is being used 5 days of the week. Sources are arriving online and may be assigned to a day of the week, where that source is routing 1 unit of flow to a designated sink. Right, so we want to assign a source to a day of the week such that the network is not being overloaded on any given day. It's a flow scheduling problem. And so I've just listed out 3 assignment problems that hadn't quite been attacked by previous frameworks. And the contribution of our paper is that we provide 1 minus 1 over e competitive algorithms for these problems. Sometimes in special cases, but most of the time unconditionally. Okay, so that's the upshot of the results of our paper, but let me say a little bit about how we do this. We do this by attacking a single problem called a submodular assignment problem. And so I've written the corresponding linear program on the left here. But the setup is as follows. We have a ground set of edges E. An edge E has a value E and a VE and a cost BE. And E is partitioned to parts P1 through Pn, where we can take at most 1 edge from each part. That's kind of the assignment part of this problem. And the submodular part is that Bx must satisfy submodular constraints. And at this point, I wish I had written down the definition of submodular here. I sort of forgot to do that, but I encourage you to pull up Wikipedia and Google that real quick if the definition of submodular is something that escapes your memory right now. But these exponentially many constraints are where the submodular part of this problem comes in. And now to make this an online problem, in the online version of submodular assignment, your parts are arriving online one by one, and we have to maintain a solution to this linear program online. Now, I'll say there's one caveat. We will have to allow what's called free disposal, which means that, when a part arrives, that's when you have to decide what elements you take. But you are allowed to dispose of any elements you've taken so far. You just can't add anything back. But you're allowed to freely dispose of things. And this is just an artifact of the fact that edge-weighted online bipartite matching also needs a free disposal assumption, or else you provably cannot get a good competitive ratio if you don't allow this assumption. This is certainly necessary. And the point I really, sorry, a question?
Can I interrupt you for a moment?
I wish you would, please, go ahead.
Submodularity is important. And normally it's defined in terms of a lattice with a join and a meet.
Mm-hmm.
I just want to check that the lattice you're talking about, for example, is in the partial. You're talking about vectors Bx.
Okay.
Yeah. Maybe just a word about what submodular means in this context would be helpful.
That's great. Okay, that's a great point. So yeah, online submodular assignment is in itself a very abstract problem. We pose it as this because it captures a lot of problems. But there's a special case that I really like called online matroid intersection. And there, this submodular function is replaced with the rank of a matroid function. And so, for example, I like to think of the graphic matroid as a very particular example where maybe my ground set of edges are actually the edges of a graph. And now f of s, the rank of a set of edges, is going to be the number of vertices that those edges span minus the number of connected components that those edges form. So yeah, so I think looking at specific combinatorial examples of a submodular function f is a good idea. My favorite specific example is the graphic matroid, just the set of acyclic subgraphs of a graph. And you replace this f with the rank of it, which in the graphic case is the number of vertices spanned minus the number of connected components in that graph. Okay, so those are some concrete examples. I will talk a little bit more about like the nice matroid intersection case. In fact, this whole talk is going to be on just like maybe like a specific matroid example, because that's my favorite toy case. But if people have more questions and want more examples, I'm more than happy to talk about that. Just wanted to say the general framework that we tackle for the sake of the paper. Okay, perfect. Yeah, so this is the general framework. And so with this framework, let me just say exactly what our work and our results are. In this online submodular assignment model, you have the parts that are arriving online. We have Oracle access to f of s, just pretend we know what f of s is at all times. And we have this free disposal assumption. Our result here basically is a fractional 1 minus 1 over e algorithm for the variant where you're allowed to put fractional values on the x's. And a corollary of this is that for the original integral problem, just the submodular assignment problem I said earlier, you have a balance type algorithm for this with an extra small bits assumption, which I can get into. Our second result is an integral 1 minus 1 over e algorithm for some special cases. Okay, but with that, let's get into actual examples of submodular assignment problems that are maybe a little bit more tractable to work with. So I like to look at matroids as a special case. As a reminder, a matroid is just a set family of special sets. Okay, it's over a ground set E, and it's a very nice set family with two good properties. One is that this set family is downward closed. We call this set family independent sets. So if A is an independent set and B is a subset of A, then oh, whoops, that should be B is also an independent set, forgive the typos. And then we have an exchange property, which says that if A and B are independent sets, but B is a larger independent set than A, then there's a way to take an element from B and add it to A that preserves independence. Right, so there's all sorts of great examples of matroids. Linear algebra gives one good example, where you have a ground set is a set of vectors, and your independent sets are those subsets of vectors that are linearly independent. Right, you can really see the exchange property in action with the linear algebra example. There's the graphic matroid, which is one I've talked about earlier and is in the slides. The edges of a graph are your ground set, and the independent sets are acyclic subgraphs. And then we have the partition matroid, which is one that we've actually talked about a lot. It's just where your ground set is partitioned into parts P1 through Pn, and the independent sets are precisely those with at most one element from each part. Okay, so these are the objects that I actually want to work with in this talk. Now the submodular function f is replaced with the rank function. So now f of s, or rank of s, is really just the size of the largest independent set that is in S. That's what the rank function is. Now, like I've said the general problem, but I think it is instructive to just think about matroids for the rest of this talk, and maybe even more specifically, your favorite example of a matroid. Okay, any questions up to this point? Okay, I think I'm doing okay on time. Okay, good. So this particular special case I want to think about is what's called matroid intersection. It's nothing more than the sets that are an independent set in two different matroids, one a partition matroid and another an arbitrary matroid M. So in this model, we have, again, these n parts are arriving one by one, and you can pick at most one element from each part. But it is now that we want what we pick to be an independent set in a matroid M as well, right? So this is the online matroid intersection problem. Parts are arriving, we pick an element from each part, and we want an independent set in M. Okay, so that was just like an exposition on the problems that we solve. But now let's go a little bit back to matchings, and I think this is a very fun section of the talk. I'm going to talk about this really phenomenal, beautiful proof that was iterated over for many years, fractional online bipartite matching. So even if you didn't quite get the abstraction I was talking about earlier, I think this is like a very fun proof to take a look at, and it will set the groundwork for the type of techniques that I do in my paper as well. Okay, so in fractional online bipartite matching, same setup. We again have ad slots arriving one by one, and we have to allocate this ad slot to advertisers, but the caveat is that we can allocate an ad slot fractionally to neighboring advertisers. So for example, maybe I give a third of mass from this ad slot to each advertiser, right? This sums up to at most one. I can do the same thing with the second advertiser. Maybe I give half to each of these. And then when this last advertiser comes in, I can only give a sixth mass to this last advertiser because it's already 5/6 full. Okay, so this is fractional online bipartite matching. And I will give you a great algorithm for fractional online bipartite matching called water filling. And it turns out this algorithm is actually optimal. In the water filling algorithm, the setup is as follows. We're going to think of every incoming vertex as a unit of water, and we're going to think of every advertiser as an initially empty bucket of water. So what do we do when a unit of water arrives? The water filling rule states that we allocate water to neighbors at lowest water level at any point in time. So for example, right now, all of our buckets are empty, so we're going to allocate water continuously to each of these three advertisers up until they're full, like 1/3 full. Another unit of water arrives. What is the neighbor of lowest water level? Well, there is a neighbor at water level 1/3 and a neighbor at water level 0. So we're going to start by allocating water to the fourth advertiser all the way until it hits water level 1/3. But now two neighbors are at lowest water level, and so the rest of the water is going to be allocated to both of them equally. And so then this is how the unit of like mass is allocated. This is how water levels act. What's cool about this algorithm is that it is actually optimal. It achieves 1 - 1 over E. Not just for this online bipartite matching problem, but for a lot of variants of it. The edge weight, the AdWords, the general assignment. It's really a broad algorithm that works in a lot of scopes. And what my paper shows is that it's not going to be a matching phenomenon. It's going to end up being a submodular phenomenon. And so it can be applied even broader. Does the algorithm make sense? Water filling in itself? Sort of? Okay. Please feel free to ask me to go over it again. I spent like so long on this animation. I had to like animate tiny epsilon with rectangles and like move them up and then select each one to like come up at the right time. So I'm very proud of this animation, and I am more than happy to play it again if anyone needs it. Okay. Now let's get to the actual geometry of the problem. I talked about a combinatorial problem, a combinatorial algorithm, but here is where we're going to use linear programs to actually show that the algorithm does well. Right? I've introduced you to what's called the primal linear program, the original linear program that describes the original problem we're interested in. There's a dual for every linear program that is nothing more than just playing a game of finding the tightest upper bound you could possibly get for your primal program. Really, I think the takeaway from weak duality and primal duals is that this program is a game for us to find the best upper bound for our original linear program. And weak duality basically states that for any feasible solution X to our original program, and for any feasible solution alpha beta to this program, it turns out that the objective of X can be upper bounded by the objective in alpha and beta. So I'm kind of glossing over like primals and duals, how these things are made, et cetera, but really like just keep this weak duality property in mind if you haven't looked at linear programs yet. Weak duality just says that a feasible primal X and a feasible dual alpha beta, the value of the dual upper bounds the value of the primal. That's all. And this is all we're going to use for our analysis. How we're going to use it is as follows. I'm going to look for two desirable properties. Right? So when an online vertex arrives and we're doing our water filling algorithm, we change an edge ij by delta. What if, for our first desirable property, we had a way to mirror some changes and maintain a dual such that the dual changes by exactly the same amount that the primal changed by? Okay, so that's this first property. The change in our primal solution that the algorithm did, we can match with a change in the dual solution of our own. And what if at the end, I looked at my dual solution and I found out that alpha I plus beta j, precisely these dual constraints in the dual linear program, is at least gamma. You know, if gamma was 1, we'd be really happy, because then I have a primal that has value equal to the dual, but then weak duality says that a feasible dual always upper bounds my primal, and so that means that my primal is optimal. So we would be really happy if gamma was 1 at the end of this paradigm. Okay, that's probably asking for too much. But what if gamma is big? You know, what if gamma is, say, 1 minus 1 over e? That would be enough to get a 1 minus 1 over e competitive algorithm. So that's basically the paradigm we're going to have. We're going to have something where we make changes to our primal, and we make changes to our dual that's matched. And at the end, our dual, maybe it's not feasible, but it's approximately feasible. That's going to be enough to prove a gamma competitive algorithm. Okay, so the first part, so we wanted two desirable properties, right? The first part's going to be really easy. You know, say in our water filling algorithm, we've allocated delta to an edge ij. What dual variable should we change? Maybe alpha I and beta j. And so the question is, how should alpha I and beta j change? We're going to have to, you know, divvy up delta among alpha I and beta j. And I think at this point, it would be really natural to be like, okay, we'll just give half of delta to alpha I and half of delta to beta j. That is a splitting procedure that certainly maintains this property that change in the algorithm is equal to the change in the dual, but it doesn't quite work. It's actually just going to yield you with a half competitive analysis, which is like so sad because it's such a natural splitting procedure. And I could write out the counterexample, but really I think I'll just tell you the spirit of the example, what the example tells us. Is that half-half splitting procedure is not enough. As a vertex gets filled, it's more and more urgent that we increase the dual variable of that vertex. And that is why we motivate the following splitting procedure. We're gonna allocate a piece of delta proportional to this g of x function, basically saying that we increase alpha I proportional to how filled it is. You know, if it's very close to being filled, a lot of mass should go towards alpha I, and then the rest should go to beta j. So I know the splitting function is probably like a little bit mysterious. Honestly, they just kind of like in the analysis, you can just be like, we split it somehow, and then you can go back and find out what value of g you would actually need. But end of the story, we basically just have a way to split delta among alpha and beta. That is how we get the change in the algorithm to be equal to the change in the dual. And so now we're like halfway done. I swear we're like very close to a 1 minus 1 over e competitive analysis. Just this slide is all we need to finish the analysis. We just need approximate feasibility. And so that brings us to the question, right? If we look at these dual constraints for feasibility, for each edge ij, what is alpha I plus beta j? There are two cases. You know, j is an online vertex. What if j did not route all of its water? That implies that I must be full, right? Because if I wasn't full and j still had water to route, water filling tells us it's going to route water to I. And now this is where the magic of G comes in, right? How this is just looking at what alpha I is going to look like. This is the analysis for alpha I. Alpha I is being raised at a rate proportional to its water level. And we know that last water level is 1. And so that means from 0 to 1, it's being raised at a rate of g of x. And g of x is precisely this function, and that gives us 1 minus 1 over e. Alpha I, actually, in this case, is 1 minus 1 over e. Not even the sum, just alpha I is. That's actually kind of the easier case. And what if J did route all of its water? Now, this is where we really use the key water filling property, which is that J is only routing water to offline vertices of water level at most the final water level of I. Right? Like J is only ever routing water to the lowest water level. So this is true. And what that gives us is it gives us a lower bound on how fast beta J is rising. Right? If we have an upper bound on the water level that J is routing to, that gives us a lower bound on how beta J rises. And so we can kind of do a very similar analysis. The first term on the left is alpha I in a very similar manner to how I did on the left. And this term is just 1 times the rate that it's growing at, which is at least 1 minus g of final of I. And that again gives us 1 minus 1 over e, which is kind of amazing. And so maybe this starts to, like, in hindsight, shed light as to why we wanted this g of x function, where this g of x function comes from. You can just optimize for g of x, given that you know that you're trying to like maximize these quantities. Okay, so that was the water filling algorithm. At this point, I can like stop for a few minutes and like take questions. If you want to go over some part of the proof again or anything, this is like, I think one of my favorite proofs, so I'm happy to talk about it. And it sets up the groundwork for the proofs that I do. So please feel free to ask questions. Okay. If this makes sense, I will talk about some of my work as well then. Okay, so given that the context of fractional bipartite matching, this is a great time for me to sketch the proofs for how this might work in matroid intersection. Right, and just as like a reminder what this looks like, we have a ground set of edges E that are being revealed one by one, part by part. And when a part arrives, we can choose at most one element from the part. This is kind of like the partition matroid of the matroid intersection. And we want to pick elements such that we're forming an independent set. And right now for fractional online matroid intersection, it just means that we want to maximize the size of our fractional common independent set, which is described precisely by this linear program. Right? This linear program says that for every single subset S, the mass that you have on that subset is upper bounded by the rank. This is what it means for something to be a fractional common independent set. Okay, so this is fractional matroid intersection. I want to do the same thing as we did before. I want to do water filling, but like right now it's not entirely clear what water filling might look like. Before we had, you know, offline vertices, each were like a bucket of water, and then you could route to the smallest bucket of, you could route along an edge that led to the least filled bucket of water. Here we don't really have offline vertices anymore. We just have these exponentially many constraints. You know, like what would be your water levels? That is not entirely clear. And once you define a water level, then the water filling algorithm is natural. But to define these water levels for this exponentially defined program is a little bit, at least to me, it wasn't immediately clear. There's a few different wrong paths you could go down. But I think the coolest part of our paper is we devote like an entire section to describe submodular water levels. And we come up with not 1 or 2, but 3 beautiful definitions of water levels that are all equivalent, and make a primal dual analysis of like a fractional online matroid intersection and submodular assignment in general, very clean. And so I'm going to take you through a few of these gorgeous submodular water level definitions. The first one I think is maybe the most natural or combinatorially defined.
Number 1 is your ability to move on. This is very important because people think that when a breakup happens, you have to prove yourself to your ex. That couldn't be further.
Hi, is someone not muted?
Indo?
Oh yeah, sorry.
But back to water levels. So I think this definition of water levels is maybe the most combinatorially motivated. Here I'm going to go through a specific example with the graphic matroid. And the idea is as follows. We're going to define a water level for every edge. Every edge now has a water level. The algorithm to find these water levels is as follows. We're taking it as input a vector x, and we're outputting a water level vector of 1 for every, or we're outputting a water level for every edge. The first thing we're going to do is we're going to look at this ratio. Right? If we looked at before at the linear program for matroid intersection, it was like x of s always had to be less than or equal to rank of s. Well, let's look at what's closest to tight. Like what maximizes this ratio, right? That number will be rho, and you can find a unique maximal set S star satisfying this ratio rho. The fact that it's unique just follows from some modularity, but basically you can find this set S star that's like closest to being filled, and elements in S star have water level rho. We're going to contract S star and repeat. That's it. And so, for example, in this graphic matroid here, I have written down the x values on the edges, and like kind of how bold the edge is proportional to how like filled it is right now. So you can just take my word for it, but it turns out this edge right here, this single edge right here, is the unique maximal set S star in this first iteration. So I'm going to assign it water level 0.9, and then I'm going to contract it. Okay, so when I contract that edge, this is kind of like what the graph looks like now. And again, you can take my word for it, but it turns out these two edges here, the 0.3 and 0.5, are my set S star in this next iteration. So 0.3 plus 0.5 is 0.8, divided by what the rank of these two edges is, which is just 1. That's the largest acyclic subgraph you can get with just these two edges. Okay, so that means that both of these edges get a water level of 0.8. We again contract. Turns out the rest is the next maximal set S star. And again, we get 0.4. So this is how you make the water levels for just the specific graphic matroid case. But yeah, this is a combinatorial algorithm. I'll give people a second if they have any questions about this algorithm. The upshot of this algorithm is we're finding a way to succinctly describe what elements are closest to being filled. It made a lot of sense before in matchings, describing how filled something is. Like, well, it's the offline vertices you're saturating, so of course, maybe we should assign saturation and water levels to offline vertices. And here, we have found a way to describe how filled like a linear program is with this kind of combinatorial approach. I think that's a nice upshot of this. But there are many definitions of water levels. Another one we came up with is just by solving the following concave program. So if U is an optimal solution to this program, then the water level of an edge E is actually precisely XE divided by UE. And what's really beautiful about this is it's going to follow from constructing an optimal dual solution satisfying the KKT conditions. And that optimal dual is actually coming from the combinatorial decomposition I said in an earlier slide. That's how we prove that these two definitions are equivalent. What I like about this concave program is that it's not really a new thing exactly. Like a program very similar to this arises in models of markets and algorithmic game theory. So this is like market equilibria game theory motivated, and maybe has a very beautiful connection to some of the techniques used in that field. Okay, and with that, I've like given a few definitions of water levels. Let's do the water filling algorithm now, because we have everything we need for that. I mean, the water filling algorithm now is just when a part QJ arrives, you should just continuously allocate water to elements at the lowest water level, right? Because now I've defined a water level for every element. This is the filling algorithm for that. But if that's like maybe a bit too, intuitive, you could also solve the following concave program, nicely motivated by the definition of water levels I had on a previous slide. And if we remember in the proof of fractional online bipartite matching, the crux of that was this water filling property. And so I want to make sure I state that. What does that look like in matroid intersection? Here, it looks like, what I want to hammer home here is that it looks like complementary slackness. If XE is bigger than 0, then WE is the minimum water level among QJ's elements. And if J did not allocate all of its water, if there's slack in this constraint over here, then that means the water level of every edge is 1 for all elements in QJ. What I really like about this box is that water filling is now thought of as complementary slackness in a concave program or a linear program. I think that's what's cool about this. Okay, so we have like the tools, we have the algorithm, and now I'm going to finish us off with the analysis. It's going to very much mimic the like nice analysis I said earlier for fractional bipartite matching. But of course, to do the analysis, we need to take a quick look at the programs again. We have this primal program. The constraints here just say that this is a common independent set. It's satisfying the online constraints that we're picking one edge from every part, and it satisfies the matroid constraints, which say that the value on every set S is at most the rank of S. This is the primal program we're interested in. And then the dual for that is this. You can just take my word for it. But we again have these alphas and these betas, and the name of the game is to create a dual that's roughly feasible, maybe not entirely feasible, but like approximately feasible, that has value the same as the primal. But like this dual is big. There are very many alpha S's here. There are, as many betas as before, but there are like exponentially many alpha S's. And we're trying to like, minimize this objective. So we, probably can't just assign value to any alpha. So I think a critical question when looking at this dual is which sets do we assign a positive alpha S to? What's nice about all the algorithms I took us through for water levels is that it gives us the answer to this question. At the end of the water filling algorithm, what do we have? We have a feasible solution X, whatever the algorithm gave us. But we also have the water levels that arise from a nested family. And this is exactly just the combinatorial decomposition I had before. This set comes first, then this set comes next, and then this next set is last. It's the level sets of the water levels. That's our nested family. And these are precisely the sets that we're going to assign positive alpha value to. Okay, I'm going through this. I think I'm doing okay on time. So I'm happy to like take questions if people have anything at this point.
It looks to me like people are not asking questions when you ask for questions, but they ask you during other times.
That's it's totally fine. If there are no questions at this time, happy to take them offline. Or if like people want to go back like 10 slides and have something they'd like to clarify, also happy to do that. Okay, so right now we're trying to do the primal dual framework. We have some ideas about how we set the duals. Now let me put that in concrete terms. How do we change the alphas and betas when we have a change delta to an edge E? Right, our algorithm increases E by delta, and now I have to change alphas and betas that match delta, right? So just as before, while part J is routing water to element E, we're going to change beta J to be 1 minus G of this water level of the edge. And at the end of the algorithm, we have this nested family that we're going to set the alpha S's as. We're going to set it to be the following. So here, the alpha S of this outermost set is going to be the integral from 0 to the first water level. And then the alpha S of this set here is going to be the integral from the first water level to the second, and then the innermost set gets this as well. And we set the alphas like this so that we get kind of this nice property of the alphas, that this variable, which exactly mimics this summation in our dual constraint, has a simple expression, which is just the integral from 0 to the water level of E of g of x. So this is just like a very clean way to make this summation nothing more than maybe just this intuitive aggregate that we've had with the bipartite matching case. So admittedly, with how I set the duals, it's not actually clear that the change in the primal is equal to the change in dual. Like, I changed beta as J was routing water, but then I changed alphas at the end. It's not actually clear that I have the value of my primal is equal to the value of my approximate dual. That's harder. That's something, if you were captivated by this talk, you can look at the beautiful presentation of it in the paper that we wrote. Some of the tools that we use to get these guarantees are as follows. What I like about our section of water levels is that we prove some beautiful properties about water levels along the way. We show that water levels are monotone, that they have some indication of feasibility. The water level is less than 1 if and only if it's a feasible primal. There's this locality where as XE changes, the water level is roughly stable. And then there's this duality property here. This is the Laplace extension of a submodular function. But this duality is how we show that our change in primal is equal to change in dual. Just kind of glossing over some of the buzzwords in our paper. So primal is equal to dual is a little bit harder, but approximate feasibility, by how I set it up, is basically the exact same as fractional bipartite matching. Again, 2 cases. If QJ did not send out all of its water, that must mean the water level of E is 1. This is the indication of feasibility property that I had in a previous slide. And so this beautiful summation, which is in our dual constraint, will give us, again, 0 to 1 of g of x, which is just 1 minus 1 over E. If QJ did send out all of its water, then by the water filling property, complementary slackness, whatever it is you want to call it, it sent out water to elements of at most E's final water level, and that gives us a lower bound to how quickly beta J filled. And so again, we have this summation of alpha S is 0 to water level of E of g of x. You add it to 1 minus g of final V. It is the same algebra as in the bipartite matching case. So approximate feasibility pops out in the exact same way once you've defined water filling and the water filling property with the right notions. And so that concludes the analysis that I'm going to go over. That concludes all the proofs I'm going to go over. The last thing I want to talk about, just for the last few minutes, is the integral results that I've proved in some future directions. So this slide is going to be dedicated to how my problem is similar to a sister problem called online submodular welfare maximization. And the setting there is that you have some buyers, you have items. The items are arriving one by one, and buyers have utility for the items. And our objective is to maximize the sum of the utilities. Now, when the utilities are submodular, this is called online submodular welfare maximization. Hugely popular problem in the field. People love this. But people had their hearts broken when it was proven that there is no polynomial algorithm that can do better than half unless NP is equal to RP. And it turns out greedy is just going to get half on this. So really, this problem, it's like a little bit intractable past the trivial algorithms. What I think is really cool about this problem is that it's not exactly similar to our problem, except in a special case. When the FIs are matroid rank functions, it then becomes a special case of our problem. And then we have a 1 minus 1 over E integral approximation algorithm. And so what we've done is we've created this sort of separation between submodular utility and matroidal utility. Our paper can solve and beat half if you have matroid utilities, which is a special case of submodular. And honestly, this integral case captures a lot of the really pretty problems we talked about. It captures matroid coloring, so the online arboricity problem I told you about, flow scheduling. It captures B matchings. It captures a lot of cases. But embarrassingly enough, it does not capture laminar matroids. And so maybe like a toy case that's really been frustrating me is, can you get a 1-1 over E competitive algorithm for online bipartite matching with just extra laminar constraints on top? Has not been solved yet. But this at least captures a lot of the really fun cases. Okay. And so this is my last slide, just a little bit of a summary of what it is we do. We've shown that water filling water levels are not really matching phenomena or assignment phenomena. They're submodular phenomena. And with that, we have captured like a broad scope of fractional and integral assignment problems. And we've, pushed the limits on how general an algorithm like this could be. And for future directions, the submodular assignment problem is an interesting problem in its own right. Just understanding like what it looks like integrally offline is like one natural question. The offline generalized assignment problem has a 1-1 over approximation ratio. And then just online, as we've been doing it, what is the best competitive ratio there?